Okay, so in this video we're going to talk about the introduction to volumes by revolution. So in this one we're just going to introduce the disk method and the washer method. So let's talk about the disk method. So what you want to think about is I have a given function, like f of x looks like this, and I'm rotating around the x-axis. So this one here I'm rotating this way. So if you keep rotating, you get a diagram that looks like this. It's a cone rotating this way. So you get a cone that looks something like this out of this diagram. So that looks kind of like what it is. So this is my function. This is my y-axis. This is my x-axis. I rotate, I get a cone. Okay, so it looks like a cone. So if you rotate around the y-axis, the x-axis, you get this. It looks like a cone. Now, if you use the same diagram, you're rotating this way, and this becomes my y-axis, this is my x-axis, I still get a cone. But the way that you look at it is going to be different. So again, like cross-sections, the way you do it, depending on how you do it, depending on the function, you shouldn't get the same volume unless it's like a symmetric equation. Like in that case, y equals x. If you rotate this way versus this way, you should get the same volume. Okay, so in this case, that's how it is. But later on, we'll talk about how if you rotate on a different axis, like you rotate over here or up here or down here, that will give you something completely different. But that's in the next video. Okay, so in this case, I'm rotating this way. I get this cone-looking thing. So I purposely drew this out over here. Okay, it rotates this way. That means I am going to go this way. So that means my cross-section here, this diagram over here, would look something along this line. Okay. Because it's just go away how you do it. Rotate this way, you get this way. Now if you rotate this way, naturally it's going to be like this. Okay? So this part here, that is just the disk method. So the area of essentially what you're having is, this is my radius. Okay? If I keep rotating this way, so in that case it's just going to be pi r squared. Okay? So my area is basically a circle going from this way all the way over there. So it's pi r squared. Now, you may be wondering, like, what is the radius? The radius is the function, top function minus bottom function. I don't have the bottom function, so I have just going to be f of x. So it's going to be f of x squared times pi. That will be my area. That's going to be my integrand for my solids of revolution. If I integrate with respect to y, in this case, I'm going this way now, but this one, it's going to be pi times f of y squared. So in essence, is that this method, your cross sections essentially is just going to be the ones over here. Okay, these are all circles in that regard. So if you cut it out, you should look something like this. So this is a rectangle. Okay, so in that case, it should have circle, 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 just kind of like the cross section thing we talked about earlier. Okay, so that's my diagram over here. So in that case, my cross sections are perpendicular to my axis of rotation. So I'm rotating around the x-axis. That means it's going like this, so it's going to be perpendicular. Okay, if I'm rotating this way, I'm just going to be horizontal because it's perpendicular. Now, both of these are cones, but they have very different volumes because of the given function, both depend on the given function. Okay, so in that case, to find the volume of the solid, it's going to be the integral of a of x dx between a and b, or the integral from c to d of a of y d of y, depending on which way you're rotating. Okay, so this is very similar to the equation we use for the volume by cross-section. Okay, but this one here is just by solids of revolution. Same idea, but it's just the integral of area to get volume. Okay, so likewise for the washer method, it's very similar. In that case, we call it a washer is because when we have something like this, for example, this is what a washer looks like. Okay, this is a washer. So I have an inner function and an outer function. So in that case, because I have this is my outer function, this is my inner function, so that just means if I rotate, I should have a hole somewhere in the middle. So the way you distinguish between a washer and a disk has a solid volume. Like there's no holes anywhere in between. But for a washer, if you integrate this way, rotation here, you have this part which becomes some area, becomes a hole of some sort. So this is completely solid. But this one here, you have holes in them. Okay, so in this case, my washer method, likewise to my cross-section and my area between curves, it's just going to be the top function, my bottom function. If I rotate around my x-axis, okay, I get a cone-looking thing on the outside because of this part, and this part inside, I will have things that curved in. So this is my inner function. So you have something that curves in, okay, because again, rotation, curving, okay. So if I rotate around this way, okay, again, it's similar to that. So in that case, because of the way this looks, it's going to look like this, x, and it's going to be y. So likewise, washer and disk methods, both are, the cross sections are perpendicular to the axis of rotation. Okay, so rotate this way, my diagram looks something like this, so my diagram looks something like that. So that's a good way to help you remember. Okay, rotation, and you have that. So the difference now is, for we have a washer, you have outer function and an inner function. So in that case, outer function, if you rotate this way, you have the outer function and the bottom function. So essentially is just, again, pi r squared. Okay, so my radius here is going to be, my radius would depend on the f and the g in this regard. Okay, so in that case, my outer function for this one is this function, my inner function is like this. So if I rotate this way, my outer function minus my inner function, that's my radius. So that's how you can get a of x is equal to pi times f of x squared minus g of x squared. Okay, so in that case, that's how you do it. Now, if in terms of y, turn your head 90 degrees, this is the top function, the bottom function, you rotate this way, this is the outer function, this is the inner function, so this radius is dependent on f squared minus g squared. So essentially it's just pi times f of y squared minus g of y squared. So, in essence, very similar to this. This is a to b of a of x, d of x, or in c to d, a of y, d of y. Okay? So in that case, again, this is going to be a to b, this is going to be c all the way to d. So if you're integrating with respect to y, you have to use y bounds. If you integrate with respect to x, you have to use x bounds. So that's what these things are. Okay, so let's go through a couple of simple, straightforward examples that basically feed off these, and then that's going to be the end of this video. Okay, so the disk method. So f of x is 1 minus x. That's my diagram. And it's between 0 and 1, and we're rotating around the x-axis. So in that case, I'm rotating around this way. So because we're rotating around the x-axis, and we know it's perpendicular to the axis of rotation, so that means it's going to be this way. That's what the diagram is going to look like. Now, because this is a disk method, and we're rotating between 0 and 1, so in case this is from 0 to 1. So my volume, my area here is equal to pi times this function minus this function. In that case, f of x squared, because area is equal to pi r squared. So that means my volume here is between 0 to 1 of pi times f of x squared. That's what it is, dx. Okay? Now, if I'm rotating around this way, okay, that means, again, perpendicular to axis of rotation. In that case, it's going to be horizontal in this case. So in this case, again, we just have to write that function in terms of what? In terms of what? So that means for this function, we end up with, let's get a red marker, we have y is equal to 1 minus x. That means x is equal to y plus 1. So this function here is y is equal to 1, oh, whoops, my bad. X is equal to y plus 1. That's my f function, f of y. Okay, so that's what it is. Okay. So again, my area here is equal to pi r squared. So area is equal to pi. My function, because we didn't go with respect to y, would be again 0 to 1. Because just by plugging in the numbers, you get 1. Plugging in, you get 1. So in case my radius here is going to be this function and the y-axis. So it's going to be y plus 1 squared. So that means my volume here is equal to, from 0 to 1 of pi times y plus 1 squared dy. And of course, you just have to go ahead and integrate that, and you get the volume. Okay? Now, washer method, again, similar to this. Okay, I think we just picked functions for this. So, we already drew the picture. So this function is f of x is equal to x. F g of x is equal to x squared. Now, because it's a washer method, I'm rotating around the x-axis. Okay, rotating around this way. That's what my diagram looks like. Again, my cross sections are perpendicular to my axis of rotation. We end up like that. That's what it is. Now, again, area is equal to pi times the top function squared minus the bottom function squared. So in that case, it's x squared minus x squared to the power of 2. That means my volume here is, again, between 0 and that point here. Equate them, so 0 and 1. So in that case, volume is between 0 and 1. And you have pi on the outside, you have x squared minus x to the power of 4 dx. Okay? So you might be wondering, like, why is this way? The way you want to think about it is the outer radius minus the inner radius. So in that case, the way you want to think about it is just going to be A is equal to pi f squared minus pi of g squared. I'm just combining them together. You have the outer radius and the inner radius. Okay, so now let's come back to this washer method thing. Okay, same diagram, same function, but we're doing rotating around the y-axis. So in that case, rotating around there, and because its cross sections are perpendicular to the axis of rotation, so we have horizontal. So again, we have to write these functions in terms of y. So this one becomes x is equal to y, x is equal to square root of y. We're taking the positive y, square root of y, because this is going in the positive direction of y. So my area here is equal to pi times f. Okay, let's just label this. This is square root of y. This is y. So this is f of x, f of y. This is g of y. Okay, y is equal to g of y. In that case, top function and the bottom function. So in that case, f of y squared minus pi times g of y squared. So we know the volume is equal to pi on the outside because we just factor pi out. We're going from 0 all the way to, in this case, 1. So 0 to 1. And then we have function y, so it's square root of y squared minus bottom function, which is y squared dy. Okay, so those are the examples for disk and washer method. Okay, in the next video we're going to do a couple more examples with this. But things to take away. Both disk method and washer method, the cross sections are perpendicular to the axis of rotation. That's number one. Now, number two is whenever we get a function like this, go ahead and draw the direction where you will have to integrate. Okay, that's number two. Number three, set it up. This method is solid. Washer is you have holes in it. So usually this one you have two functions, and this is given by just one function. Okay, number three, when you draw it up, draw the function, draw the two functions, find the intersection, okay, and then draw the axis of rotation. If you draw that, that just helps you to verify that you have set it up correctly. And then that's it. Okay. In the next video, we'll do a couple more examples, and then in the next video, we're going to do where you shift the axis of rotation to somewhere else. Okay, so that's it for this video. See you in the next one.